and exactly one positive real root. The other option I can have is this has the full 3, which means I have no imaginary solutions, no complex imaginary solutions. And this are the only 2 sets of answers I can get. The really, really nice thing about this is because I got 1 for Descartes' rule of signs, because I got 1 for the positive real roots, I am guaranteed a positive real root. So I'm hoping beyond hope that it happens to be a rational number. But if not, the intermediate value theorem can help me with that. So I'm going to focus on positive real numbers with, I'm going to come back up here, the rational root theorem and the remainder, or I guess that's test, right? Rational root test and remainder theorem to find the rational roots. So my leading coefficient, my a sub n is 1, and my a sub naught is negative 12. So a sub n equals 1, and the constant is negative 12. And so these are the things that make up my rational roots, my p's and q's, right? Remember, we got to mind our p's and q's to find our possible rational roots. And so what we want to do is we want to make the list of all factors of 1, well, that's not too bad, and all factors of 12, which also isn't too bad. And what we're going to be looking at is the 12 over the 1s, right? So we say this was our p's and this was our q's. So all my factors of a sub naught are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. And all of my factors of a sub n are plus or minus 1. So I have 1, 2, 3, 4, 5, 6 numbers. With their plus or minus, I have 12 things to choose from. But I am focusing only on positive, because I know I should have 1 and only 1 positive. So knowing I'm guaranteed that because of Descartes' rule of sign helps me run this search a little more quickly. So our possible roots are going to be these numbers, right? Because p over q, it's everything over 1. So our possible roots are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. And so those are all the possible rational roots that could be answers to this. They're the things that we multiply to give me my constant coming out of this from the leading coefficient. So the remainder theorem will help us choose these. So I need to grab my initial polynomial. I'll rewrite it back down here, still in blue. F of x equals, where is this ugly thing on my paper here? Flip a page over, flip a page back. Where did it go? Ah, there it is. X to the 4th, coefficient of 1. And x to the 4th, 2x cubed. There we go. X to the 4th plus 2x cubed plus x squared plus 8x minus 12. All right, so my remainder theorem says if I take a number and put it into the function, if the result is 0, then that is a root. So I want to start with all my positives. 1 to the 4th plus 2 times 1 cubed plus 1 squared plus 8 times 1 minus 12. So that's 1 plus 2 plus 1 plus 8 minus 12. 3, 4, 12, 0. So my first root, x equals 1. All right. I'm going to use synthetic division because I have an x equals 1. And I'm going to simplify this problem. I'm going to move from a 4th degree problem to a 3rd degree problem. I'm really hoping to get to a 2nd degree problem because that will let me use the quadratic formula. I have one of my real roots, so I have to find a negative root out of this. And what I'm hoping to do is to make a simpler function to use the remainder theorem on. Right? I don't want to be plugging 12 to the 4th in here, so I'm going to use a simpler function. So my coefficients are 1, 2, 1, 8, and negative 12. So I'll bring down my 1, I'll multiply. I'll add, and then I'll multiply. Alright, so we're doing the multiply, multiplied by each term, adding across our lovely synthetic division. So I'll put in 3, I'll add, do my last multiply, 12. I should get 0 because I knew this was a factor, and there's no remainder. So my new polynomial is x cubed plus 3x squared plus 4x plus 12. And if I were thinking of where it came from, this root here is equivalent to the factor of x minus 1. And if you want to check when you're reviewing your notes, this would be a good time to multiply this back through and see that you get to the x to the 4th polynomial. But for me now, this is the thing I want to use. And I have my positive root, so I need to find my negative root. Or my negative roots, right? There's 1 or 3 of them. 1 or 3 of them. So I'm going to use the remainder theorem on this now. And I'm going to rename it g of x just to distinguish it from the initial polynomial. Just to have 2 different names. Nothing special, no reason why I wanted to call it g. And I'm going to use these roots, 1, 2, 3, 4, 6, and 12, but I'm going to use their negatives. So negative 1 cubed plus 3, negative 1 squared, plus 4 times negative 1, plus 12. Right, and our remainder theorem, this is g of negative 1. Our remainder theorem is we're hoping this is 0. Negative 1 cubed is negative 1. Negative 1 squared is positive. So we get 2, negative 2, positive 10. So negative 1 is not a root using the remainder theorem.
Oh my God, Katie!
Using the remainder theorem. Again, be happy with calculator for these things. Calculator makes the remainder theorem go relatively quickly and makes it a lot more useful. When I first did these, we had to do these calculations by hand, and the powers of 4 just can get annoying, especially with things like 12. 12 times 12 is 144, but then 12 times 12 times 12, right? And then in 12 times 12 times 12 times 12. All right, let's look at negative 2. Then we're just going to keep working through our possible roots. But I'm just going to use the calculator to give my result. So I'm going to put negative 2 in. So I'm going to put this in parentheses on the calculator, and I'm going to work the answer through as it comes through. So -2 cubed plus 3 times -2 squared plus 4 times -2 plus 12, and I get 8 for that. Now I will use an up arrow on, my calculator, and I'll just go through and replace in my parentheses all my -2's with -3's. Hold on 1 second, guys. You can just set it there. Thank you so much. Sorry about that. A package just came. And I am on the porch. I did say that would be the weirdest thing about the porch. Hopefully it's my camera and I can start recording calculator stuff. Many apologies. This does become 0. So I now have my other root, x equals -3. So we now have 2 of the answers. In 2 steps, we've gotten 2 of the answers to this polynomial. We know x equals 1 and x equals -3. Now what I want to do is I'm going to use synthetic division with this and with this to get this to be quadratic. That way I can use the quadratic formula. So I'm going to take -3. I'm going to take my coefficients from g of x. So I get 1, 3, 4, 12. I'll bring down the 1. -3 times 1 is -3. That gives me a 0. -3 times 0 is 0. Bring down 4. -3 times 4 is -12, which gives me a 0. That means this last polynomial is x squared plus 4. And this is nice because I know that the only roots this can have, because the positive sign here and no x term, is imaginary. And so I'll say x squared plus 4 equals 0. X squared equals -4, or x equals plus or minus 2i, right? And we made this quadratic. Whew! That's a blackboard full of stuff. I'm going to walk back through it all and see how all these pieces go together and where this is coming from and where it's going. So we start here. We have a 4th degree polynomial. I need 4 solutions. I'm going to use Descartes' rule of signs to tell me how many are positive, how many are possibly positive, and how many are possibly negative. So Descartes' rule of signs says there's definitely 1 positive real root, and there's 3 or 1 negative real roots. So I put this into a table of all the possibilities I can get, knowing that if I get imaginary results, they come in pairs or 2s. It's a guaranteed 1 positive real, and I'm either going to have 1 or 3 negative reals, which means I can have 2 imaginary or 0 imaginary. Each row has to add up to 4 because that's what the fundamental theorem of algebra is telling me. I've got to have 4 things determining the zeros or the roots here. So I use the rational root test using the constant and the leading coefficient to find the possible rational roots. I plug the positive ones because I know for sure there is exactly 1 positive. So as soon as I find it, I'm done. And I found my positive real root at 1. Now, I don't want to keep working with a 4th degree polynomial. So I have one thing it is divisible by. So I divide it by that one thing to make it a third degree polynomial. And I named my third degree polynomial g of x. Now, it can only have the roots from the rational root test up above. In fact, the only thing that tends to happen here is the leading coefficient becomes something else, and you can throw away some possible roots. But in this case, not the leading coefficient, the constant becomes something else, and you can throw away possible roots. But you never gain any more. So I have simplified my polynomial down a degree. So I use the remainder theorem again, and I work my way through the negative roots, because I have found my only one positive root. And I find that -3 is another root. Instead of dealing with the third degree polynomial, I use synthetic division, and I now have a quadratic. And this quadratic is in a form where I know it's going to be imaginary. We should have seen these in our quadratics. It has no middle b term, so I'm looking at, if I look at it in quadratic formula terms, there's no b, so it's 0 plus or minus the square root of -16/2. Right? Plus or minus, because that's my b is 0. 0 minus 4ac, a is 1, c is 4, -16. And that will give you the same thing here, if you want to use the quadratic formula. And so our goal has always been to reduce these things down. And so all of my solutions for x, I have x equals -3, x equals 1, and x equals plus or minus 2i. And I have now found all 4 solutions. Only 2 of them cross the x-axis. And I'm going to put this one up here so we can see that on how it manifests itself. So what did we have here? We had x to the 4th plus 2x cubed, x to the 4th plus 2x cubed, plus x squared plus 8x minus 12. And let's bring it over here. And so here's this function on our graph. We have the 2 real solutions, and the imaginary is kind of giving it an inflection point out here somewhere. Right? Because it dimples instead of being a nice parabolic. And the imaginaries are influencing it out here. But if this was part of a polynomial equation, I would have my solutions. And that's what we're working our way towards, is solving polynomial equations. So we now have a toolkit where any degree polynomial I can break down into linear or quadratic things. And I can state every time it crosses the x-axis. And as we did with quadratics, as we did with linears, that place where we cross the x-axis is a solution. So we now have a toolkit where we can deal with polynomial equations. We can do polynomials that solve things, that model things, and we can find the places where they give us answers. We can also describe them in more complete terms. And so what ends up happening is real life data. The models we like to use tend to be quadratic because it has a clear minimum or maximum. But when we have complex data points, we will get large polynomial solutions coming out of them, large polynomials with different coefficients. And we will tend to use that model from the data to predict future behavior. And so we will want to set things where we can find where they turn to 0. And so we're going to kind of look at the idea of polynomial equations. And I kind of want to work on the intermediate value theorem a little bit more. We covered it very lightly on how we would find rounding. And let's look at a polynomial equation, and I'll move into that, because finding things that aren't perfect rational numbers are useful. There's some tricks we can get to get everything to be rational numbers, but knowing how to get our repeating decimals that aren't fractions, I'm sure to say not repeating decimals, but our pi's and our e's and these irrational numbers, square roots of 2 and square roots of 3, to come out will be helpful. So I'm going to clean up here because I filled up the blackboard. I'm going to highlight, because I don't think the book summarizes this really well, is that the fundamental theorem will tell you how many things you're going to be looking for. Descartes' rule of sign is going to tell you how many of those could be positive or could be negative. You put that together with the fundamental theorem and you'll be able to tell what types of roots you're looking for. And once you have what types of roots you're looking for, keep track of what you're doing. Right? When I knew there was only going to be one positive and exactly one, get that out of the way, because I don't have to use the remainder theorem on any other positive number once that's done. And always, whenever you find one root, divide your polynomial down. Divide your polynomial down, because as soon as you hit quadratic, the quadratic formula will help you, and you will be able to find your imaginaries there. Sorry about that. That's one of the things about working on the porch. So let's look at equations instead of polynomials themselves. Not a huge change here from what we're doing. So let me clear this out. Am I still on that graph? Let me get off the graph, back to the blackboard. Let me erase this. Let me put up the new one. There we go. All right, so in essence, if we have a polynomial, f of x, polynomial equation is I give it some value. I'm looking for when the polynomial returns a very particular value. And so we can find factoring as a way of solving quadratic equations. We can find factoring as a way of solving these equations. What we can do is create a new polynomial out of it. So I'll just continue in alphabetical order. G of x is going to equal f of x minus c. And if f of x is minus c, then that whole thing is equal to 0. Right? If I subtract c from both sides, I get f of x minus c on the left-hand side. On the right-hand side, I get 0. And so we create a new polynomial equal to 0. So, for example, now let me get a slightly better. Grab the wrong example. Does not have the constant I want. Let me put my example in orange red here. So I have 4x to the 4th minus 5x squared equals 9. I have some relationship, some model. So we're going to say the original function f of x is 4x to the 4th minus 5x squared, right? Some temperature model. I don't know. For me, temperatures, 4th power happens a lot. With temperatures, the way radiation works, 4th powers come out of it a lot. And this is some law of cooling. It's some model we have. And we're looking for whenever the answer is 9. So we're looking for when f of x equals 9. So we can look at the whole thing, 4x to the fourth, 5x squared equals 9. Well, I can subtract 9 from both sides and get it to equal to 0. Why do I want it equal to 0? Because when I factored, those roots and solutions were the places where the function equals 0. And so this thing on the left-hand side here now, this 4x g of x equals 4x to the fourth minus 5x squared minus 9. Well, the zeros are equivalent to the solutions of this equation. So we spent all this time factoring and looking for when our functions cross the x-axis, because if we can set our function equal to 0, that gives us a solution. And we go, well, but things don't always equal 0. And notice, this does not equal 0, it equals 9. But if I subtract that 9 from each side, I make a new thing, a slightly different function that equals 0. And this new thing is the function we solve. So that's why we spend so much time breaking down functions, looking for when they cross the x-axis, and why I use the words roots, zeros, factors, solutions. Because they become solutions to equations. And they're how these things can solve out. So this is the function we're looking at. Now, I'm going to use this one here to show you a trick. And this trick is very useful. Instead of going through all of Descartes' rule of signs, going through the fourth power and dividing this down 2 times to get it quadratic, I want to notice something here. Notice this is counting by 2's. In fact, it looks very, very similar. It looks amazingly similar to a quadratic, right? What's our quadratic? A x squared plus bx plus c equals 0. Right? I'm counting 2 times this. We're going to do a thing called substitution. And substitution, and I think this is always the best place to show substitution. All of mathematics is taking something you don't know what to do with and making it look like something you've done before. That sounds simple, but it's complex, right? We had 7 or 8 rules that we started out with, a plus b equals b plus a times b equals b times a plus the parentheses b plus c equals parentheses a plus b, right? Our commutative rules, our associative rules, our distribution rule, our identity, a plus 0 equals a times 1 equals a, our inverses. And by manipulating all of those rules, we get everything else we've been doing. And one of our big things that we did was, hey, a line crosses the x-axis somewhere, and we can solve for that. And so we've been breaking down our functions into their linear parts. But occasionally, we get things that don't cross the x-axis that matter, these imaginary things. So we needed to study quadratic things. And so with polynomials, we've been breaking them down to lines and quadratics so that they can pull apart. And so this idea of making harder problems look like a bunch of easier problems you've done before is really the tricks of mathematics. Each trick is a little bit different. Substitution is one of those. The thing about substitution in general is until you've done a whole bunch of substitutions, they're hard to see sometimes. And they can be a little bit confusing. But what I kind of look for is these are counting by 2's or multiples of 2's. Whatever this is times 2. Notice the power here is 1. 1 times 2 is 2. The power here is 2. 2 times 2 is 4. And so we say this is quadratic in form. It has the 3 terms. Whatever the middle power of the middle term is times 2 gives you the leading term. So it would be nice if I had another variable, our substitution variable. I'm going to do a bright green. And I want to change this by saying, hey, what if u equals x squared? I take another variable. I'm going to substitute with it. So if u equals x squared, then u squared is x squared squared. But my power rule says that's x to the 4th. Well, that's good because I have an x to the 4th here and an x squared here. So I can rewrite this whole thing in terms of u. So I'll get 4, it's my leading coefficient, x to the 4th. Well, x to the 4th is u squared. Minus 5 x squared. But x squared is u. Minus 9 equals 0. So what we're recognizing, and I'm going to go slow and overly emphasize things, might jump up and down a bit. If I had my chalkboard going, you know, might pound on the blackboard a bit, right, for overemphasis here. But this is quadratic in form. And we find the substitution that lets us write this as a quadratic. Which means I can now use my quadratic formula to find u. So I'm going to a equals 4, b equals negative 5, c equals negative 9. So u is equal to negative b plus or minus b squared minus 4ac over 2a. Right? So u is equal to negative 5 is 5, plus or minus negative 5 squared is 25, minus 4ac. So minus 4 times 4 is negative 16. Negative 16 times negative 9 is what, 144? Positive 144 over 2 times a, which is 8. So I get 5 plus or minus the square root of 169 over 8. Right, 25, 144, 169, yep. And I think the square root of 169, if I hopefully remember correctly, is 13. So I get 5 plus or minus 13 divided by 8. But those are my answers for u. And I wanted to know x, not u. So let's work out these answers. So if u equals x squared, let's put these in. So I'll give my two answers. 5 plus 13 is 18, and 18 divided by 8 is one of my answers, right? 5 plus 13 is 8. 5 minus 13 is negative 8. And so my two answers for u is 9/4. Oops. or -1. Double check me. I mean, I'm double checking myself here, making sure that all of these add through. 5 plus 13 is 18. 18 divided by 8, that's right for the 2a, that's 9/4. 5 minus 13 is -8. -8 over -8 is 1. Alright, that works. But u is equal to x squared, and I want x. So x squared equals 9/4, and x squared equals -1. Notice I took the two u values I've got and I plugged them back into here. So this tells me x is equal. Somehow I seem to have gotten mine upside down. Oh no, I'm in the right place. Yep. I take the square root of both sides and I'll get a plus or minus, right? When I take the square root of both sides, I get a plus or minus, and the square root of 9 is 3, and the square root of 4 is 2. Right? I'm taking the square root of both sides, I get plus or minus 3/2. Take the square root of both sides here, and I get plus or minus I. So, using the idea of an equation format, we can factor our functions, and we can find what x would be on our original equation. So this is why we do all this factoring, why we do all of this root finding. So my initial equation is this. I get the equation so it's equal to 0. That lets us treat the left-hand side as a function. And with functions, when they equal 0, those are the roots, they're the divisible parts of it. And I use this particular function to show the trick of quadratic in form. This is quadratic in form. And substitution is how we do that. The substitution will work. There are some things we'll do where we'll have odd powers, like let's see if I can scroll down here. Where this comes in really, really useful a lot of the times is x to the, let's see, let me see if I can remember one here. X plus x to the 1/2 plus 3. That's the same as if u equals x to the 1/2. Then this is u squared plus u plus 3. So the substitution will come in even when we're not dealing with polynomials. In fact, I think the book writes these equations as x plus the square root of x plus 3, which happens a lot. Square roots talk about distance to things. Square roots are ways of undoing a series of multiplications, right? We just did a square root in solving the u up above. So square roots will pop back into our equations. Substitution lets us find answers without having to work with the square root part initially. So this substitution is a nice thing to learn. And I think in this part, like the book shows this by going, hey, you can factor this. This is a factorable thing. You pull it apart and they use the tricks of factoring on it. Underneath that idea of factoring, I like to highlight substitution. It is the most useful, it is the only trick you have been using in algebra and mathematics. You have been substituting something else in for the problem you don't know what to do yet. And every little trick you have piled up is some form of substitution. We just pile up so many of them that they become these methods that we use for doing certain things. All right, I told you I was going to continue this week doing chapter 4 up to section 5. We have covered all the bags of tricks on how to solve equations, how to factor polynomials. There is one thing I'm going to start the next class with, which is section 4.4 in the book on the intermediate value theorem and estimating answers. How to estimate answers. The book only touches on this a little bit, and it relies on technology. I'm going to show you how to do it a little bit by hand and the technology side by side. So it's going to take about a half hour, and that's a little more time than we have right now. And we're going to focus on the word problems that get us all the way up through section 4.5 in the book. So we'll be finishing 4.5 at the end of this week, and then finishing the rest of the chapter next week. Coming across, and then that'll leave us the last week of April and first 2 weeks of May to do chapter 5. And chapter 5 conceptually is a really tight nugget coming across. And you'll probably at the end of next week I'll do a little bit of function algebra. I will get the tests scheduled for chapter 4 up on Pearson. I will get a practice test similar to the practice test there. Please email me any questions you have on the homework. Please start digging through the homework on chapter 4. In fact, just email me anything you need, right? Don't sit there and avoid. Reach out. I am trying to, my email's getting quicker and quicker responses. So hopefully I should be turning around email a little more quickly on everyone. Yeah, I think I'm going to leave it on that. Be safe, be well. If you need anything, shout.